Hi there. In this video, I'll be talking through section 14.2, which is actually broken into two parts. So in the notes, I have 14.2 and 14.2b, so just be aware of that. So a lot of this I'll talk through rather quickly. We saw a bunch of it in class, and some of it, the ideas are very simple. So if we have a circle and a center, anywhere in this plane, and throughout this section I'll be assuming we're working in a single plane. If I forget to say it, it's not a trick. Every point in this plane has a certain distance from the center. By definition, every point on the circle is at some specified distance called the radius. If the distance is less than the radius, it means we're not as far away as the circle is. We're somewhere in this zone, which we call the interior. So this stuff that I'm shading in blue, the inside is called the interior. And formally it's defined as the points where the distance from the center to one of these points in the interior is smaller than the radius. This distance here is smaller than the radius. If I have some point where the distance is bigger than the radius because it's farther away, all of that stuff we call the exterior. So it's inside and outside, but we have a formal definition using distance. Now our definition of the tangent of a circle is a line in the plane of the circle that intersects in just one point. So something like so. If I position this just so, there is just one point of intersection, and we call that the point of tangency. The line is not crossing through the circle, it's simply touching. And we can use this word tangent a little bit loosely. So tangent can refer to the line. Sometimes we'll just call it a tangent. Sometimes we'll call it a tangent line. But we can also use the word tangent as an adjective to describe this situation. The line and the circle are tangent, or are tangent to each other. Or we can say the circle is tangent to the line. We have some flexibility there. Okay, now a couple of theorems about the relationship between a tangent and a radius. So if I take a circle, a line perpendicular to a radius at its outer edge. So I'll start by drawing a radius. Here's my outer edge. And now if I draw a new line that is perpendicular to that radius, what we're seeing here is that this line I just drew is a tangent line. I'm not going to prove that, but hopefully the picture speaks for itself. A line perpendicular to a radius at its outer edge is, I'll say, tangent to the circle. And the converse works the other way. So I'll wind up drawing a picture that's almost identical, but we're starting with slightly different information. We also have that every tangent to a circle, so if I start with a tangent line, it says every tangent to a circle is perpendicular to the radius drawn to the point of contact. So if I draw in this radius, it is a guarantee that this must be perpendicular. So it sort of goes both ways. If I start with a radius and a right angle, I get a tangent line. If I start with a tangent line and a radius to the same point, I get a right angle. And then finally, we'll extend this word tangent. It actually gets extended in a lot of ways, but here we're just going to say what it means to say that two circles are tangent to each other. So what it means is that they're tangent to the same line at the same point. So I could have one situation where here's a circle, here's a line, here's the point of tangency, and then I'll draw a different circle that's tangent to the same line at the same point. Something like so. You'll notice I could hide the line, and it just looks like the two circles are touching in a single point. They're not crossing each other, they're simply touching. Another situation is I could have a circle like so. Here's my tangent line and my point of tangency. And then maybe my second line looks something like so. Gotta move it just right. Like that. Also, two circles touching each other in just one point. The situation here on the left, more specifically, we would say that these two circles are externally tangent. And here on the right, we would say they are internally tangent. The circles only touch in a single point, but their interiors maybe overlap or maybe don't overlap. So this was mostly vocabulary in this first part. Now, if we switch to the second part, so we'll just call this more from section 14.2. So I'm not going to go through all of the proofs here. Some of them I'll talk through, some of them will actually be left as exercises. But the big takeaway I want you to realize is that things that you already know about congruent triangles can transfer into facts about circles. So let's look at this example. The perpendicular from the center of a circle to a chord bisects the chord. So if I start with a chord, here's the chord AB, and here's the center of the circle C. And suppose I draw in a perpendicular like so. So what we can prove is that this chord this segment that is perpendicular to the chord bisects it. We could prove that AD equals BD. And just to walk you through the sketch of that, so just the sketch of the proof. What if I draw in the segment CB and the segment CA? These are radii of the same circle, so they're congruent. So CA equals CB. And CD is congruent to itself. So we could use hypotenuse leg to show that this right angle, angle ADC, is congruent to this right angle. So, sorry, this right triangle ADC is congruent to this right triangle BDC by hypotenuse leg. So then you can see, oh, well, we have perfect symmetry between these two triangles. Using CPCTC, segment AD would be just as long as segment BD. Right, so there's a lot of symmetry that we get in circles. Next theorem. A segment from the center of a circle to the midpoint of a chord, which is not a diameter, is perpendicular to the chord. So this is basically the converse of what we just saw. So if I start with a circle and a chord that is not a diameter, so here's A, here's B, here's the center of the circle C. And suppose here is D, the midpoint of that chord. If I draw in this segment, we can prove that segment CD is perpendicular to the chord AB. And maybe you can see how to do this. The trick is to unleash what we know about triangles. So if you draw in segment AC and you draw in segment BC, we have two triangles. And moreover, anytime I have two radii in the same circle, those are congruent. So maybe you can see how to finish this. I'm not going to do it, but there are congruent triangles hiding in that diagram. And that would probably let us prove something about perpendicularity. Another one, this one I'll just draw a picture. In the plane of a circle, the perpendicular bisector of a chord. So if I start with this chord, and then I draw its perpendicular bisector, the line that is perpendicular to that segment and goes through its center. Hopefully you believe that along this line, if I extend this purple line, it goes through the center of the circle. I didn't even start by drawing the center, but hopefully you can see that the center would be there on that perpendicular bisecting. And a corollary that we could use here, I'm not going to dwell on this. This is something that probably feels very obvious but might be tricky to prove, is that no circle contains 3 different collinear points. Another way of saying that is no line intersects a circle more than twice. So I think that's very believable if you take a circle and start drawing some lines. Right, here's a line that doesn't intersect at all. Here's a line that intersects twice. Here's another line that intersects twice. Here's a tangent line that intersects once. But no matter how hard you try, you're not going to find a line that intersects that circle 3 times. And that is provable as a corollary to this theorem, but I'm not going to worry about the details. Quick definition, which you would probably assume. Ooh, forget about that. If we use the word congruent to describe circles, we mean circles with congruent radii. So they're circles that are exactly the same size, and we measure the size of a circle using a radius. So a couple more theorems here. In the same circle or in congruent circles, chords equidistant from the center are congruent. So let's suppose I have a pair of congruent circles. So these 2 circles are exactly the same size. And let's suppose that I have chords that are equidistant from the centers. So here's a chord, and here's a chord. So here's A, here's B, here's C, here's D. Here's X, the center of this circle. Here's Y, the center of this circle. Now we're saying the chords are equidistant from the center. Hopefully you remember that if we have a line and a point, by definition, we measure that distance according to a perpendicular. So we need some more letters. Here's E, here's F. So we're given that EX and YF are the same distance. What we want to prove is that the chords, segment AB and segment CD, are congruent. And again, the trick is to use radii and look for congruent triangles. If I draw in this radius, and this radius, and this radius, and this radius, not only are these 2 radii congruent to each other, but because the circles are congruent, all 4 of these radii that I've drawn are congruent. So now again, hopefully you're seeing, oh, all right, well, between these 2 circles, I see congruent triangles. So there's a symmetry here, and presumably if I'm careful with my CPCTC steps, I could use that to ultimately show that the distance from A to B is the same as the distance from C to D. Here, theorem 14.8 is basically a converse. If I have a circle here, and a circle here, and they are congruent. If I have 2 congruent chords, so let's suppose here's the chord AB, and here's the chord CD. If I start with the fact that those chords are congruent, we can prove, and let me actually move those markers a little bit. So if we start with these congruent chords, those 2 congruent chords will be equidistant from the center. So here's the center x, and I draw in this perpendicular to measure distance. And here's the center y. And I draw in this perpendicular to measure distance. What we'll be able to prove is that those distances are the same. And how are we going to do that? Well, we're going to look for congruent triangles. Hopefully you see that if I draw in all four of these radii, all four of those segments will be congruent to each other, and presumably I can use things that I already know about congruent triangles. Okay, just one last little thing here. This theorem, I'm not going to prove it, but it's one of these theorems where it says something very obvious, but it's nice to know there is a proof. I'm not including it. You can ask me about it if you're curious. This is called the circle line theorem. So it says if a line and a circle are coplanar, and the line intersects the interior of the circle. So here's a portion of the line, and it's definitely going through an interior point. Then, what we know is that this line intersects the circle in two and only 2 points. It intersects in exactly 2 points. And that should be pretty obvious. If I extend the line in this direction, there will be 1 point over here where it intersects the circle. And if I extend the line in this direction, there will be 1 point over here where it intersects. This is actually harder to prove than you would think. There's some very famous theorems in math where the fact is really obvious, but it took some very smart people a very long period of time to actually prove it for sure. This is sort of that flavor. The proof is more complicated than you would think, but the idea is definitely true. If this feels right, I'm telling you that it actually is correct. Okay, so I've gone through this kind of quickly. Some of this you'll be practicing in class, but that is it for now.